All right, so this week we're going to be covering limits plus limit laws. So our goal today is to figure out what are limits, so our goal today is going to figure out what are limits, and then we also want to figure out how to solve. All right, so first thing we need to go ahead and and figure out is what exactly is the definition of a limit. So we can go ahead and define a limit So a limit is going to be something, it's going to essentially be whenever we try to find, it's going to be whenever we approach some x value called A, and that shows what y value called L, and we approach some y value and then L essentially helps us show exactly what the behavior of the function is at and near A. All right, so now that we have that, let's go ahead and look at our actual limit notation. Our limit notation is essentially going to be defined as, let's say we have some function f of x, well, we also know that we have our limit a, and we want to find the limit as x is approaching a. So we'll write it like this. Our limit as x approaches a is going to equal that value L. So yes, so like I once again saying, what this says is as x infinitely approaches a, it approaches some value on f of x called L. So it's important to note that we're not necessarily looking at s equals a, but what happens when x approaches a. So let's go ahead and look at some ways that we can go ahead and start solving for our limits. The first thing we can do is we can go ahead and use tables. So let's go ahead and say we have some so once again, like I said, we're looking at the behavior as x approaches a and not necessarily at x equals a. So let's go ahead and look at the function f of x equals x squared minus 4 all over x minus 2. So let's go ahead, we can go ahead and create a table, and then now we're going to find the limit as x approaches 2 of f of x. Well, as we can see right here, if we go ahead and just kind of look at this 2, we can see if we plugged that straight in, we get 2 minus 2 in the denominator, and that would give us a 0 in the denominator, which is a big no. So we have to use limits to go ahead and see what the behavior of this function is whenever we get close to x equals 2. So first thing we can do is we can go ahead and build a table. So let's say we have our x values here. We have our f of x here. So now let's go ahead and just start writing down some values that are at or near 2 on both sides. So let's go ahead and say we enter 1.9. And at 1.9, our f of x is going to be 3.9. We can get a little closer and go 1.99. And there we get 3.99. We can go a little closer and go 1.999. And there we get 3.999. So now let's go ahead and just say what happens when we are at x equals 2. Well, like we said earlier, if we go at x equals 2, that gives us a 0 in the denominator. So our function would not be defined at that point. So we'll just write undefined. Now let's keep going a little further on the other side, since we can kind of get an idea right now of where our limit at x equals 2 is approaching, but we need to go ahead and make sure we check both sides to make sure that there's nothing weird going on with the graph. So let's go ahead and look at 2.001. Well, right here we get 4.001. Go a little further out, 2.01, we get 4.01. And just one more point, just to double check, we get 2.1 and then 4.1. So as we can see, as we're increasing, getting ever closer to 2, we also get closer to our f of x equals 4. And the same thing happens when we go from the other side. As we get closer and closer and closer to 2, our f of x once again approaches 4. So therefore, we can go ahead and just look at this table, and we can be able to pretty easily tell that our limit of x squared minus 4 over x plus 2 as x approaches 2 is going to, in fact, equal 4. All right, so now that we have that out of the way, we also have to remember there's a couple little stipulations that we need to go ahead and be careful of when we're estimating. In some cases, you'll have some sort of function, and then this is usually going to happen whenever we have an oscillating function. Sometimes this will happen when we have an oscillating function. So oscillating functions they usually tend to jump between two different y values, and they jump very rapidly. So, for example, this graph would look something like this. So if we get closer and closer to 2, if we get, let's going to find at x equals 0, the limit as x equals 0. Well, this jumps around so fast around x equals 0, there's no way we could be able to properly estimate that limit. So that's one situation where you're going to have to be careful of, especially if they're going very, very quickly in a very quick succession. Now, sometimes they'll have oscillating functions such as your sine and cosine function, but those aren't so crammed around one point to where you could actually be able to look at different pieces. So like if you have something like this is easy to tell the behavior since everything's not so crammed together. Is that if that makes sense? And then we also need to be careful about just plugging in just plugging in your value into the calculator, because in some cases, but not all, the limit of x approaches a of f of x does not necessarily equal our f of a. So that's just something to keep in mind of. And so a lot of cases it does, and we'll go over into more detail about when it does work, but that's something you also need to be aware of. Essentially, so the difference is we use, once again, whenever we're paying attention to limits, we are paying attention to the behavior as x approaches a. All right. And then you also need to be careful with estimation as well. Because you also have to be careful. Pretend that's an R. Because sometimes estimation can be misleading. This usually happens whenever you don't get close enough. So like for example, let's say like you have a graph and you're going from, like, let's say you're trying to find the limit as x approaches 0, and let's say you keep getting closer, like you start on your approximation. So let's say you start your approximation at x equals 1. And you go ahead and go down to x equals 0.01. Sometimes that can show a certain behavior, but you may get the wrong, but sometimes it'll give you the wrong impression, especially if the actual limit is very, very small. You may have to go even closer and closer and closer. So that's just another thing to be aware of. All right. So now that we have those little disclaimers out of the way, let's go ahead and move forward. Now let's think of some ways that are always going to be foolproof, though, whenever we're looking at limits. Because, like I said, estimation, it's helpful, but you also have to be careful when you're estimating. But let's go look at something else that will be a little bit more helpful. Let's now pay attention to our one-sided limits. Essentially, one-sided limits are whenever you're taking the limit from only one side. So either the positive or negative side. So essentially our notation for one-side limits is so we have our left side and then that's usually that is going to be essentially our negative side. And that is going to be written in the form, the limit as x approaches a from the negative side of f of x. Then we are going to have our right side. And that's going to be your positive side. Our notation for that is going to be when you take the limit as x approaches a from the positive side of f of x. So now that we have now that we can have our definitions of one-side limits out of the way, let's see how they can actually be useful. So this can actually help us prove limit, actually be able to definitively prove whether or not a limit exists. So let's go ahead and take a scenario. So this actually brings us to this theorem. So we can prove that the limit as x approaches a of f of x exists if and only if our left-sided limit, so our limit as x approaches a from the negative, equals some value L, but it also equals our right-sided limit. So our limit as x approaches a from the positive of f of x. If all of this equals each other, so if our left side limit and our right side limit are both, if they both exist and equal the same thing, then that proves that our actual limit exists at that point on f of x, and that limit is going to be equal to L. So that actually can help us truly decide, and this is especially useful whenever we're dealing with piecewise functions. So just to kind of get an idea of how this can actually show us whether or not a limit exists, let's go ahead and let's say we have this function. In this example, we have a piecewise function, and our piecewise function is going to be our f of x, and it's going to be defined as, let's say we have our function is going to be 2x plus 3, and this is going to be defined when x does not equal 1. And then let's say our function is just going to be some constant 10 when x equals 1. So now let's go ahead and see if we can draw a quick graph of what this would look like. We know it's going to be linear, so it's going to be a little steep, so we're going to go something like this. And then actually we're just going to erase all this. Let's clean this up. But we have to take into account we have a hole right here, and that point is going to be defined way up here. So let's try to see so first of all, let's try to see if we have, does the limit exist? At x equals 1, or as x approaches 1, of f of x. And then we are also going to see, and this is also going to show why limits are so important. So first thing we're going to do is we are going to go ahead and find our individual sides. So we're going to take our limit as x approaches 1 from the negative side, and then we know that that's going to be of 2x plus 3. And that's going to essentially get us, so 1 from the negative side is going to be like 0.99999. So that's going to be very close to 1. So we can essentially say we have 2 times 0.99999, which is essentially 2 plus 3, which is going to equal 5. And then we're going to go ahead and take our limit from the positive side. Once again, since we're not technically at 1, we will go ahead and use our 2x plus 3 formula. And in this case, since we're going from the positive side, we're essentially plugging in 1.000001 for our x. So 2 times 1.00001 is going to essentially be 2. So therefore, our limit would end up being 5 once again. Since these two equal each other, then we can go ahead and say our limit as x equals 1 approaches 5. Once again, like I said, this is really important to show how limits show the behavior of your graph rather than what actually comes out. Because in this case, if we just looked at plain x equals 1, that would say our limit is 10, when in fact that's not actually very indicative of what our graph is telling us. Our graph is telling us that it essentially should be a straight line, and right here should be a 5, but for some reason or another, our piecewise function has defined this as being 10 as opposed to 5. So now let's go ahead and let's go ahead and do another similar example. In this case, we're going to have another piecewise function. And then we are going to go ahead and say that we have our limit. So we're going to say our function is going to equal 1 for all values where x is greater than 0. And it's going to equal -1 for all values when x is less than or equal to 0. So now, first of all, let's go ahead and draw this and see what this looks like. So we know right here we're going to have a little circle at 0 at 1, and then it's going to keep going forward in a straight line like this. Now it's going to be defined down here and keep going in the opposite direction. So now let's say we want to try to find the limit as x approaches 0 of f of x. So first thing we're going to have to do is once again go back to our one-sided limit. So now we have our limit as x approaches 0 from the negative. So in this case, since essentially this is saying we're having -0.001, we're going to use that bottom function. So our limit, and then since that's just a constant, we're going to just spit that constant straight back out. Now we'll go ahead and check from the other side. Our limit, as x approaches 0 from the positive, equal, and then we're going to go ahead and our f of x is actually going to equal 1. Because most of the time we're looking at 0.001, which is on the positive side, that is technically bigger than 0, so that's going to be at 1. And we see that this is going to be 1. We see that these two do not equal each other. Because of this does not have a true limit. And if we look at the graph, we can go ahead and see that there's not really a good way. Like, we can only do one-side limits at this. If we try to say what's the limit at x equals 0, then what exactly are you talking about? We can only do one-side limits. Are you talking about, because if you tell us from the negative, we can say for sure, oh, it's -1. If you say from the positive side, oh, it's 1. But there's no way we can say what our limit is at that x equals 0 without some sort of other stipulation involved. And then just a couple quick more things, and then, all right, so then next part for this chapter, for this section, I mean, we're going to go ahead and take a look at infinite limits. So now, infinite limits are essentially whenever your limit as x approaches a of f of x equals plus or minus infinity. Now this limit still technically does not exist, but it can show us why it does not exist at this point. This says it does not exist because it goes to infinity, or because it goes to negative infinity. So essentially, this is going to look something like this. Let's say we're going to find our limit as x equals 0. We can see right here that this is just a going up to infinity at x equals 0. We can't really define what this means, but we can only define that as being it's going towards infinity. And then this also just brings us to a quick discussion of vertical isotopes. Isotopes are very closely related to limits. Vertical isotopes are essentially whenever your limit is essentially the same thing as saying you have an infinite limit at a point. It's defined as the line, but this is just defining that line, the line x equals a when the limit or one-sided limit of the limit as x approaches a of f of x equals plus or minus infinity. So yeah, just remember in this one, it can just be a one-side limit. If, let's say, it seems to exist from, let's say, once again, we're looking at x equals 0. If it seems to exist just fine from the negative side, but it goes to infinity on the other side, or if one side goes to infinity, the other side goes to negative infinity, that is still a vertical isotope. All right, so now that we have that discussion out of the way, we can go ahead and move forward with our limit laws. So limit laws are essentially here to kind of help us be able to break down some of the equations and make them easier to solve. So the first ones we're going to look at are going to be our sum law, our difference law, our constant multiple law, our product law, and our quotient law. So now that we have these, let's go ahead and look and see what these actually mean in an algebraic sense. Our sum law is essentially saying if we are taking the, first of all, let's go ahead and define our stipulations. Our limit as x approaches a of f of x exists at some point L, and then we're going to call this L sub 1, and our limit as x approaches a of g of x once again exists at its own point that we can call L sub 2. So essentially our sum law is saying that we can go ahead and take the limit, that if we have the limit as x approaches a of the combination of f of x plus g of x, then that we can actually just say that we can break this down into saying we are taking individual limits of those pieces and putting them together. So we are essentially saying limit as x approaches a of f of x plus a separate limit as x approaches a of g of x. Once again, the difference law is very similar. You're essentially just changing this down into subtraction. So if we're taking a limit of these two combined and subtracting from one another, so f of x minus g of x, then essentially once again that's saying we can break that down into two separate limits. Our constant multiplier law is essentially saying that if we have some constant c that is being multiplied by our function, so we have our limit as x approaches a of some constant c times our f of x, we can essentially just pull that constant out and then multiply that by what our final limit is. So that's essentially saying we have our c times our limit as x approaches a of f of x. Our product law is essentially saying if we have them multiplied together, we can split those up into two separate ones. Essentially, most of these are saying we can just break things down. So we have f of x, g of x equals our limit of f times our limit of g. And lastly, we have our quotient law. Now this one actually does have a little extra stipulation that we have. So we have our limit of f of x over g of x we're still breaking this down into two separate limits. But our limit of g of x, or our L2 as we've defined up there, cannot equal 0. If that equals 0, then we cannot use our quotient law. So now that, and these can all be applied to one-sided limits. And then just 2 more quick laws, and then we can go ahead and start playing around with these, start doing some examples with these. So we have our 6th limit law, which is going to be our power law. And that's essentially saying that if we have our limit raised to a like our function raised to a power, we can raise our limit to the power. So if we have the limit as x approaches a of f of x to the nth, we can take that essentially out of that and say that we have our limit raised to the nth. We have our root law, which is the same thing, which is essentially the same thing, just doing the inverse. So if we have our limit as x approaches a of f of x down to some nth power, then that essentially says we take that final limit to, we can take that final limit to the nth root. And then just there's a couple quick stipulations that we have to take care of real quick. And for our power law, n must be an integer greater than, must be a positive integer. And then for our root law, if n is even, then f of x has to be positive as well, since we cannot have a negative in a square root or a quartic root or anything like that. So now that we're here, we can go ahead and do a couple of quick examples. Now that we have all of these out of the way. So first example we can go ahead and do, let's say we have some function, f of x equals 2x squared plus 3x plus 1. And now we're going to find the limit as x approaches 1 of our f of x. Well, we can actually go ahead and use all of our laws to break this down and simplify it. So let's go ahead and split this up and use our sum rule and break this up. So now we have our limit as x approaches 1 of 2x squared plus the limit as x approaches 1 of 3x plus our limit as x approaches 1 of 1. We can go ahead and take this a little further. We can go ahead and pull these constants out. So where we have, we can use our constant multiplier and say we have 2 times the limit as x approaches 1 of x squared plus 3 times the limit as x approaches 1 of x plus the limit as x approaches 1 of 1. And then lastly, we can break that first one down just a little bit more and say that we have 2 times the limit as x approaches 1 of x, this is squared, plus 3 times the limit as x approaches 1 of x, plus the limit as x approaches 1 of 1. So now we can go ahead and start putting our 1 back in and taking our limit. So now we are left with 2. Our limit as x approaches 1 of x is going to be 1, and that's going to be squared. Plus, we have 3 times our limit as x approaches 1 of x, which once again is 1, plus our limit as x approaches 1 of 1, which is just 1. And we see that this can equal 2 plus 3 plus 1 is 6. But if we go ahead and look at this format down here at the bottom, this looks very familiar. This essentially looks like if we just plugged 1 straight into our f of x. This looks like if we had just plugged in f of 1. So this actually brings us something that can make life way easier, because this is very unfun to do. So we can actually go ahead and change this to where we can make this a way simpler. We have a theorem called, or really a property called our direct substitution property. Our direct substitution property says that if we have some function f of x, and it is either a polynomial or a rational function, and a is in the domain of x, or in the domain of our f of x, then the limit as x approaches a of f of x is simply just going to be equal to f of a. So essentially, it's saying if we have a polynomial or a rational function, we can just plug that value in and go. We don't have to actually take the limit of each individual portion, or we can just plug in our value and go and say, we know that this is our limit. Just one thing to note, if you have a rational function, once again, make sure it's in the domain. So for example, 1 over x is considered a rational function since 1 is a function and x is a function. But in the function 1 over x, 0 is not in your domain. So for example, if they wanted you to find the limit as x approaches 0, you cannot use direct substitution in that. You would have to actually go and use your limit properties and find that. So now we have to move on to, let's move on to squeeze theorem. So essentially, we have a thing that is called, an idea called squeeze theorem. Now, squeeze theorem states that let's say we have three functions. We have f of, and they're all different sizes. So let's say we have our f of x, which is less than or equal to our g of x, which is less than or equal to our h of x. And this doesn't have to be for the whole function, just whenever x is near a, and our limit as x approaches a of f of x exists and equals our limit as x approaches a of h of x, then we can say for sure that the limit as x approaches a g of x does in fact equal that same L that we get from over here. This is essentially based off of the idea of interpolation. So essentially, if you have some lower value and some higher value, but those values are the same, everything in the middle also has to be the same as that. So now let's go ahead and do a sample problem of our squeeze theorem. So squeeze theorem, let's go ahead and say we are taking the limit. We want to find the limit as x approaches infinity of 2 minus the cosine of x let me rewrite that. Limit as x approaches infinity of 2 minus the cosine of x all over x plus 3. So there's not really a good way to take the limit of this as is, because cosine of x is always oscillating. So that's always going to bounce between 0 and 1. So we can't really have a definitive limit of what happens when x approaches infinity, because infinity isn't a real number that we can just plug in. So we're going to have to get a little bit creative. However, as we said earlier, we know that the cosine function is limited, that the cosine function is limited between the range of -1 and 1. So what we can do is we can actually multiply all of this times -1. So if we multiply this times -1, we are left with 1 is greater than or equal to negative cosine of x, which is greater than or equal to -1. Which brings us essentially straight back to where we were before. We're just adding a negative sign now. -1 is less than or equal to negative cosine of x, which is less than or equal to 1. Now what we can do is we can actually shift all of this up 2. And this gets us back to our numerator. If we just shift everything up 2. So now we're left with negative plus 2, which is 1, which is less than or equal to 2 minus cosine of x. And then 1 plus 2 is going to be 3. Now we have this function right here. This gives us a little bit of a better idea of where to go. And now, since we know that that 3 is always going to be bigger than that 2 minus cosine of x, which once again is always going to be bigger than that 1, if we go ahead and turn those all into fractions with the same denominator, that would still hold up. So what we can actually do is divide all of these by x plus 3. So now we actually have our initial function that we're going to find the limit of right down in here. And now we actually have something that we can go ahead and set up. We can take the limit of 1 over x plus 3. We can take the limit of 3 over x plus 3. So now let's go ahead and do that real quick. If we take the limit as x approaches infinity of 1 over x plus 3, if we have infinity down there in the denominator, that is saying that our denominator is getting bigger and bigger and bigger and bigger and bigger. And when your denominator gets bigger and your numerator is constant, you're going to end up approaching 0 because once again, that denominator is getting bigger and bigger and bigger. You're dividing by a bigger number. So that's going to be 0. If you take the limit as x approaches infinity of our 3 over x plus 3, the same concept sticks. That numerator is not changing, and then that denominator is growing at an infinite rate. So once again, we are still left with 0. Well, now we have our f of x right here and our h of x right here, and those equal each other. So now we can say for sure, since they equal each other, we can say for sure that the limit as x approaches infinity of 2 minus cosine of x over x plus 3 does in fact equal 0. All right, so now that we have squeeze theorem done, and we also apply similar concepts to squeeze theorem, it doesn't necessarily have, like if you only have 2 functions and you know one is bigger than the other, so let's say you have an f of x which is greater than g of x, that limit of f of x would also have to be greater than the limit of g of x. So this is all the review material that I have so far. Does anyone have anything they want me to go in more detail over? Or I can just go ahead and move on to some more practice problems. All right, so let's go ahead and think of some more practice problems that we can go ahead and look at. So let's see, right here. Actually, I'll go over into like the oscillating functions a little bit in more detail. So, and I'll go and use an example of this to kind of show in a bit more detail about why you need to be careful with oscillating functions and estimation. So, now let's say we have the since as we said earlier, trig functions are usually going to be the ones most likely to oscillate. So let's go ahead and say that we have some function f of x equals the f of x equals the cosine of pi over 2x. All right. So we know that this is going to move up and down, up and down. The thing is, how fast is it going, and would this make it hard to estimate anything? So let's go ahead and try to estimate what would happen at. So let's go and try to estimate our limit as x approaches 0 of our f of x. Well, we can't really just plug 0 straight in since that gives us a 0 in the denominator, so we're going to have to go ahead and try to use some sort of estimation. So let's go ahead and look at some values. And this is going to show why estimation is weird. Since this is a cosine function, this is going to end up being symmetrical across the x-axis. This is going to be symmetrical across the y-axis. So we can actually just go ahead and look at just one side of the function. So let's go ahead and plug in a few different numbers. So let's say we are going to plug in. So let's go ahead and try to take and see what happens at f of -1/5. If we have f of -1/5, then that's essentially going to give us the cosine of -5/2. And that's going to get us a 0. Wait, 5 pi. Right, the 5 pi is important. Now let's go ahead and get a little bit closer. So now we have f of -1/7. This is going to end up giving us the cosine of -7 pi all over 2, which once again is going to get 0. Now we're going to go ahead and plug in f of -1/9. We're getting even closer now, which equals the cosine of -9 pi over 2. Once again, 0. We can see that this is staying at 0 for a very long time, right? And we can see it's still staying at 0 even as our f gets closer and closer to 0. But this is kind of misleading because let's go ahead and look at some other functions. Let's plug in some other values of f that are close to 0. Let's try f of -1/4. If we plug in that, we are going to get cosine of -2 pi. Cosine of -2 pi is going to just be 1. Let's get a little closer. F of -1/8. Well, this is going to get us the cosine of -4 pi. Once again, we get 1. We can move a little closer. F of -1/12, which is going to get us cosine of -6 pi. Once again, 1. We can see that each of these are varying degrees of being very, very close to that x equals 0. But it also jumps around a lot. Some of these are 1, some of these are 0. Therefore, we can't really definitively say whether or not a limit actually exists at that point, at that x equals 0, because this function is oscillating so much. So therefore, since we can't really approach our 0 with estimation, and we can't really plug anything in, we're just going to have to say because it's oscillating at x equals 0, our limit cannot exist. Let me see. All right, I'm going to go ahead and just do a couple of sample problems, just anything, just doing some random sample problems. So it's going to do a couple, one more. Let's go ahead and do one more squeeze theorem, since squeeze theorem is usually the least fun of these things to do. So squeeze theorem, let's go ahead. We have our f of x equals sine of x over x. Now we want to find the limit as x approaches 0 of sine of x over x. Well, these are both rational functions. As we said earlier, sine of x is rational. x is rational. But if we plug this in, we just get 0 over 0, which does not help anybody. So we can go ahead and use a similar method as we did earlier with our previous squeeze problem. We know that our sine and cosine functions are both limited to the range -1 and 1. So we have our -1, which is less than or equal to sine of x, which is less than or equal to 1. Once again, since we have this set up in the numerator, if our denominator is the same no matter what, then this would still hold. So -1 over x, sine of x over x, 1 over x. Let's go ahead, we can now go ahead and take the limit of each of these. So now we have the limit as x approaches 0. Wait, this is... Excuse me, I wrote this down wrong. This is infinity. This is infinity. Regardless, this still holds. So we take the limit as x approaches infinity of -1 over x, and this is going to be 0. The limit as x approaches infinity of 1 over x, once again, is 0. Therefore, since we have that sine of x over x is in between -1 over x and 1 over x, we can for sure say that the limit of, as x approaches infinity, of sine of x over x is going to be 0. All right, so that should be it. Unless there are any last minute questions, then we can go ahead and end our session. All right, I hope everyone enjoyed our session today, and good luck on any upcoming assignments.